cloud. Yeah. So, Dr. Sakya, whenever you are ready, so please, I believe I allowed sharing screen. Could you please kindly share your screen?
All right. Let's see if this works.
It does. Thank you so much. So the floor is yours. Thank you so much.
Excellent. Okay. Thank you, Professor Kafle, for inviting me for this opportunity. As you said, I'm super busy, but I'm not that busy, right? So I'm always happy to talk to people who are excited about physics. And so this is going to be exciting, I hope, for all of you as well. So Professor Kafle asked me to talk about particle physics, and I wasn't sure what the level of your knowledge of particle physics was. So my plan is just to assume that you don't know anything about particle physics and try to give you a broad idea of what doing particle physics involves. And I guess you can find a lot of online resources to learn about the details of various programs and various ideas in physics, right? So my plan will just to be to talk briefly and give you sort of a very broad idea of what it involves. And I hope that we can spend most of the time discussing things rather than just me speaking to you one way. So let's hope that's how it works out. All right, so particle physics. So as Professor Kafle said, I'm working at DESY, and so this is the logo for DESY. Hang on, I can't move my mouse anymore, but hopefully that's okay. Right, so DESY is the National Particle Physics Lab in Germany. And the scope of work done here is very similar to the kind of physics that is done at an international lab, for example, at CERN. So DESY is very similar to CERN in that regard. We have a lot of active programs in particle physics, doing all kinds of particle physics, both theory and experiment. I'm a theorist, so I work in the theory group. And so I'll talk a bit more about theory versus experiment later on. But let's talk about physics and particle physics, right? So what is particle physics? So the broad idea of particle physics essentially boils down to trying to understand everything. So as you know, the world is a very complicated place, right? If you look at the world or the universe as a whole, there are so many different things. Everything seems so complex and so complicated. The idea of particle physics or physics itself is that, in essence, even though the world looks very complicated, when you really try to look at the details, the world is actually very simple and quite beautiful, the structure that governs everything. And everything seems to follow some basic laws of physics, and you can really break things down into some very simple things that somehow seem to explain everything. And so the program of particle physics essentially is the quest for understanding this underlying structure of everything in nature. So this is what we as particle physics physicists aim to do. So almost everything you can see in the world can essentially just be explained by this slide, right? So everything is made up of fundamental particles, and it seems like there are many, 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 but actually, when it really comes down to fundamental constituents of nature, there's only a handful. There's about a dozen or so particles that explain everything that we see in the universe and in the world today. And so on the left, you can see a picture of all these particles together. And so you have things like the electron and the quarks that make up the proton and the neutron that we know of. There are also particles that carry forces. So the photon is something that carries the force of electromagnetism. The W and Z bosons are the particles that carry nuclear forces, and so on. And at the center of it all is something called the Higgs boson, which is a particle that gives all the other particles their masses. So just these handful of particles seem to explain everything we know in the universe. And in addition to particles, there are also forces, right? So all these particles interact through different forces, and the interplay of these forces make all the structures that we see in the universe today. So there's the force of gravitation, which makes stars and planets and galaxies. There's the force of electromagnetism that essentially controls all kinds of things we see in the universe today, from this presentation, your laptops, your mobile phones, listening, seeing, being able to see things. All of this is electromagnetism. And then there are these nuclear forces, the strong force that holds the nucleus of atoms together, and the weak force that makes these things decay over some time. So there are these four fundamental forces we know of, and there are these dozen or so particles that we know of. And this basically explains almost in parentheses, right? That's why I said almost. It explains almost everything, not quite everything that we see in the universe today. And so the program of particle physics is alive because it is an almost and it is not a complete story, right? So there are many, many different reasons actually why we think this is not a complete picture of nature. And there are many crucial missing pieces that remain to be discovered before we can claim to have a complete understanding of nature. So let me briefly tell you about what these missing pieces are and why we know there are things that are missing. So the main thing that is missing is how these particles get their masses. So you might have heard that the Higgs boson is what gives particles these masses. But that is only how the universe works today, right? So if you think about how the universe was in its very earliest moments, all these particles were actually masses. So we actually don't understand how the Higgs mechanism ended up giving all these particles their masses. In other words, we don't understand what triggered the Higgs to go through this phase transition that made it talk to all these particles and make them massive at some point in the history of our universe. So this is a big unknown in our understanding of the fundamental structure of nature. And then there's also this question of dark matter. So there is this mysterious form of matter that is completely unknown to us. And all these particles that I showed you earlier together actually make up only a small fraction of the matter we see in the universe today. So if you added up everything that we see that is made up of these particles that we know as the standard model, right? So if you add up all of the matter in our planet, in our sun, in our galaxy, all the stars that we can see, all the gas, all the galaxies that we see in the universe, that would only add up to not even 20% of the total matter content of the universe. And the remaining 80%, more than 80%, is in this mysterious form called dark matter. And we call it dark matter because we don't know what it is, right? And when I say we don't know what it is, we actually know that it is not any of the other particles that we know of. So we know that dark matter is not an electron, it's not a photon, it's not the Higgs. So it is not any of the particles that we have discovered so far, and we know that for sure. So it is some new kind of matter that seems to be dark. In other words, it seems to not talk to light. So if you shine light on it, it remains dark. It somehow doesn't talk to us through any of the forces that we have discovered. So it's the most abundant form of matter in the universe, and it caused all the structures that we see today, but we don't know what exactly this new kind of matter is, and that's why we call it dark matter. So the nature of dark matter is also one of these big mysteries in particle physics that is yet to be solved. Next, there is the question of why there is more matter than antimatter in the universe. So for every particle that I showed you earlier on, there is an antimatter partner of it, which has exactly the same mass, but the opposite charge and all the opposite properties. And you know that when matter and antimatter come together, they just annihilate each other and create a lot of energy. But the laws of physics don't differentiate between matter and antimatter. So these two kinds of matter are treated in exactly the same way by all known laws of physics. And when the universe began, we believed that it had equal amounts of matter and antimatter. And yet, when we look at the universe today, we see that everything is matter and there is no antimatter. So this is one of the profound mysteries of the universe that we don't understand yet, why there's more matter than antimatter, even though at the beginning they were probably in equal amounts, and all the laws of physics seem to treat them equally, and yet we ended up in a universe where it is mostly matter and very little antimatter. So what caused this asymmetry in nature? This is a mystery. Another mystery is the so-called neutrino masses. So neutrinos were one of the particles in the chart I showed you earlier, but they actually probably don't get mass in the same way as all these other particles. So all these other particles we know get their mass from the Higgs, right? So the Higgs mechanism, we believe, gives masses to all these other particles, but the neutrinos are an exception. So we know that they don't get the masses in the same way as the other particles, and they're much lighter, so their masses are much smaller than these other particles. And the reason why we know that they behave in a different way is because all these other particles come in two forms. So if you look at an electron, it has a left-handed electron component and a right-handed electron component. And that is true for every particle we've seen, except for the neutrinos. And that's what I tried to show in this picture, right? So in nature, every particle comes in a left-handed form and a right-handed form. And when these two are linked together by the Higgs, this is how particles become massive, how they get their masses. But the neutrinos only come in the left-handed kind. We have never seen a right-handed neutrino. And so you cannot try to make them massive in the same way as these other particles. So the mystery of how neutrinos get their mass is an open question in particle physics, and it has spurred a lot of research in this area. And then there's the question of whether there is a grand unification of forces, right? So we know that there are many different kinds of forces in nature, and this all seem to be very different, right? If you look at gravity, it seems to be very different from the force of electromagnetism. It seems to be very different from these nuclear forces that can cause different nuclei to decay. And yet we have achieved partial success in unifying these forces. So if you looked at the state of physics maybe 100 or 200 years ago, then the electric force and the magnetic force were thought to be different things. And yet today, we have a theory that combines them together beautifully in the theory of electromagnetism, right? So you cannot have a magnetic force without an electric force. And we have a beautiful theory of how they can be explained with the same physics. And that's not where we stopped. So electromagnetism was then combined with the weak force. So now it's called the electroweak symmetry, where the weak force, the force that causes nuclei to decay, has the same origin as the electromagnetic force. So we have a theory of how they arise from a same underlying physics theory and become different as the universe progresses and changes. So we partially know that forces can be unified, even though they look very different. And so one of the goals of particle physics is to extend this program to include all the other forces. So the next to be unified is probably going to be the strong force, the force that binds nuclei together. And you could push it even further and think that one day we will be able to unify all these forces with the force of gravity as well, which is a very different kind of force. So the idea that all the forces can be unified in a grand unified scheme is one of this unfulfilled goals of particle physics that is also a big deal. Then we don't understand why the universe at its largest scale is so uniform. So if you look at the universe, right, you might think that it is not very uniform because here you see a star, there you see a sun, there you see a planet. So it looks like it's very different in different places, but that's only looking at a very small part of the universe. If you looked at the universe as a whole, and the universe is very, very big and vast, it turns out that the universe looks very similar at all scales in all directions. And that's a very profound mystery because the very different parts of the universe are actually so far apart that they could have never communicated with each other. So there's no way that any information could have been passed from one corner of the universe to the other. And so the fact that despite this lack of communication, they ended up looking exactly the same is also one of the great mysteries of the universe that is probably also going to be solved by some kind of particle physics description. And so there are all these different reasons why we think that the description we have of nature is not yet complete, because there are all these crucial things that are missing from the description of nature, right? And that is the program of particle physics. So particle physics has the goal of trying to fill all these gaps in our understanding of the universe. So we are essentially trying to answer all of the questions that I just explained to you. And the research happens in two different ways, right? So there is the theory side of research and there's the experimental side of research. So what theory does, and I'm a theorist, so this is what I do all day, is I just stand at my blackboard and I try to come up with theories that can provide the answers to these questions, these open questions that I told you about. And I think of how these theories could be possibly verified by different kinds of experiments. So this is the work of the theory side of particle physics. The experimental side of particle physics concerns itself with designing and making new experiments that can look for new particles, that can look for new forces, and test these theories that these theorists come up with as possible explanations for these missing links in nature. So really, there are very different kinds of people working on very different approaches to solving these problems, right? And all of these together makes up the program of particle physics. So what exactly happens in physics research? So what is the approach to solving these problems? So what we really are trying to understand is we're trying to understand the fundamental structure of things, right? So we're trying to understand what everything is made up of, how things look like if you really could break it up and look at the details. So for that, we have to look at things at a very, very small scale, right? So we're talking about things that are so microscopic that the eye cannot see, even smaller than the breadth of a human hair, for example. So many, many, many times smaller than even the smallest things. So an atom for a particle physicist is already a very, very big structure. And what we're trying to do is really looking deep into the atom, even into the nucleus and things that make up the nuclei of atoms. So we're really looking at things that are at very small scales. And when you try to look at things that are very small scales, it necessarily means that you're trying to look at things that have a lot of energy. Because imagine I'm trying to look at the structure of an atom, right? So for that, I need to send in a probe inside the atom that can go beyond this electron cloud and deep into the nucleus and even inside the nucleus, right? So if I want to probe what is inside the nucleus of atoms, I need to send in things that can tell me about it. And I need to make sure that it actually goes into the nucleus, which means that I'm essentially looking for things that have very high energy, right? So the program of particle physics, which is look at really small scales, essentially becomes a program of looking at nature at very high energies, because at high energies is when you can really understand things at very small scales. Now, high energies, you can think of it in two different ways, right? So I can do high energy physics if I set up a system where things have a lot of energy. So I can artificially create an experiment that has a lot of high energy. But at the same time, I can also think of a time when the universe itself had a lot of energy in any particular process that went on, right? So if I could go back and look at the universe at a very early time, then it was very hot and very dense. And it necessarily had very high temperatures, which means that a typical process that happened in the universe had very high energy. So the program of particle physics, from looking at very small scales to looking at very high energies, now becomes a program of looking at the universe at very high temperatures, which is essentially another way of saying we are trying to look back at the universe at very early times. So when we do particle physics, we're not only trying to look at things at very small scales, we're actually trying to look at the universe as it was when it was just born, essentially, right? So particle physics is not just looking at particles at small scales, it's also looking at the universe at a very early time when the temperatures were very high. And all these open questions that I told you about are essentially questions of the very early universe, as well as the physics at very small scales. So this is what I just told you, right? So all these different things that seem very different, small scales, high energies, early times, are actually linked together by this logic. And by understanding one thing about nature, we're essentially understanding all these things about nature. So particle physics is not just about simply trying to discover a new particle. It's actually also understanding what happened early on in the universe when the universe was just born. And it is not just collecting all the particles that come along, but also trying to put them together into a coherent story of what the universe might have been like overall, right? So it's trying to gain a unified understanding of everything that fits together. So not just figuring out the pieces, but also figuring out how they piece together, and also figuring out how that control the earliest moment of the universe, which then controls how everything else came to be today. So there are different ways of doing particle physics, as you can guess from these slides, right? So there's the question of doing particle physics by going at very high energies. And this is essentially the program of experiments like the Large Hadron Collider. So this is what the scale of the collider that you need to do experiments like this, right? So the idea is that you can push electrons and positrons and protons to very high energies. So the LHC does protons. So the idea is that if you can push protons to very high energies and collide them, you can make new particles. And so for this, you need a collider that is many, many, many kilometers in length. And so this is like a 22-kilometer collider. So you can see that it spans a lot of area, right? And so the point of doing this experiment is that you can control these beams, collide them at very precise points where you can put a detector. For example, this is a picture of the Atlas detector. And when these collisions take place inside the detector, you can then look at things that come out. And this is how you do high energy physics. And this is how you try to discover new things that might be produced through high energy particle collisions. So this is pushing the very high energy frontier. But particle physics is not just about that, right? So particle physics is also looking for processes that are not high energy, but instead processes that are very, very rare. So for example, if I try to find dark matter in the universe. Dark matter is already out there, right? It's the most abundant form of matter in the universe. So the way I can try to discover dark matter is by trying to see if it ever scatters with a particle in my detector. And for this, I don't need to go to very high energies because the dark matter particle is already out there. So what I need to do instead is find a very controlled experiment where I can see even a single dark matter particle coming in and scattering of one of the particles in my detector. And so this is the idea behind many of these dark matter detectors, which are always in very deep underground places. So this is a picture of the Xenon 1-ton experiment, which is looking for dark matter interactions in Gran Sasso in Italy. So they put this detector deep under a mountain. Everything in the detector is very precisely controlled. So the temperature fluctuations are all understood. And so every little thing that happens in there is understood, so that if there is a dark matter particle coming in from outer space, if it kicks one of the particles and transfers a little bit of energy into that particle, that will be detected by these experiments. So looking for very rare processes is another way to do high energy physics. Right? And in addition, you can also, like I said, do high energy physics by looking at the very early universe, right? So there is an entire program in astrophysics and cosmology, which is also a branch of particle physics. And the idea is that you can look at the universe, look back at earlier times, and try to understand all these things that happened early on in the universe. And so we can do that with observing light. So when things happen in the universe, sometimes they emit light. And by detecting this light, and this light might have been produced very, very early on in the universe, we can hope to infer information about how all these mysteries might have been solved in the early universe. So in addition to light, there are also other forms of energy that we can detect, right? And in particular, a very exciting and recent and growing program is the detection of gravitational waves, right? So just like light is the excitement of the electromagnetic field, gravitational waves are waves or energy ripples in the fabric of space and time itself. So this is the gravitational analog of the electromagnetic wave. And gravity can go to places where even light cannot. So light actually stops going back in the universe when the universe was 378,000 years old. So before that, the universe was hot plasma where electrons and protons were not free. So light could not actually travel freely in the universe. So all the light we see in the universe comes from when the universe was 378,000 years old or even older, right? But with gravitational waves, we can go past this and really go back to the moment of the Big Bang itself. So gravitational waves gives us this really powerful way to look back at the universe and understand different things that might have happened there, like when dark matter was produced or when the baryon asymmetry was produced, so more matter was produced than antimatter. So all these events might have produced some gravitational waves in the early universe. And today we can, in fact, hope to detect these and infer what happened early on in the universe through things like this. So I was hoping to not talk too much. So this is actually all I had prepared, and I'd rather listen to your questions and talk to you. So just to sum up, right? So particle physics is the program of particle physics is just a program of understanding the underlying structure of everything we see in the universe. So it's a very broad research program with a lot of different directions. And as I told you, particle physics concerns itself with physics at very small scales, but also physics at very high energies, also physics at very high temperatures, which happen at the earliest moments of the universe. So it's also concerning itself with things that happen at the very beginning of the universe. And so the program is not just about discovering new particles or new forces that might be there, but actually understanding how they all fit together with all the other particles that we know of, and really trying to come up with a unified description of all the physics that we see in the world. And this is also a description of the very earliest moments of the universe when it began, how it evolved from that point on, and how it gave everything that we see in the universe today. So this is my super quick, I think 22-minute intro to the program of particle physics. And I intentionally saved a lot of time so that you could ask questions and we can discuss more things. So thank you.
Good. Thank you so much. It's a very nice, great presentation. What questions do you have? Like Leo has a question, Leo?
So I remember in one of the earlier slides, you talked about how you could group forces together. What does that actually mean? What are like implications of that?
I didn't catch it fully, so maybe Professor Gaffe has to repeat it.
So in one of the slides, you group the forces together.
Yes.
So on what basis? What is your question?
Like, how do you do it, and like, what are the applications?
Yeah. How do you classify the forces?
I remember how he talked about how he grouped the electromagnetic and I think I forgot which force it was.
So probably in the like unification process, like electricity, magnetism, and electromagnetism, and then electroweak. Like how did that? How was that combined, right?
Yeah.
Yeah.
Like, what are the applications?
What are the applications of that? That's what Leo
Yeah,
asked.
no, that's a great question, right? So it's a two-part question. One is how we unify them. What do I mean when I say particle physics can unify the forces? And part two was what are the applications of that, right? And so when I say unification of forces, so forces by themselves look very different for many reasons, right? One is so let's look at the electromagnetic force and the weak force, for example, right? So electromagnetic force is carried by the photon, which is this thing in top left of the orange circle, and the weak forces are carried by the W and Z bosons. And they look very different because the photon is massless, the W and Z bosons are massive. So that is one crucial difference, right? And the other is that their interaction strengths are very different. So the photon interacts with a strength that is very different from the strength of a W and a Z boson. And so just by face value, it looks like they are completely different forces. So what I mean when I say these are unified is that you can write down a theory where they are essentially coming from the same kind of description of particles. And so now this becomes a bit technical because now you really have to go to a PhD program in physics for 2 years before you can fully understand this. But the idea is that you can write down a theory where they can be expressed in the same way through essentially how fields transform in abstract space. And that tells you that they behave in exactly the same way, and the Higgs mechanism will then combine them two and make the photon massless, whereas the W and the Z are massive. So before the Higgs comes in, they look exactly the same, and they can be described with the same physics. And the Higgs somehow mixes them together in a way where the photon becomes massless, the W and the Z become more massive, and then they look different from there on. But we now understand how to write down a theory where they look exactly the same. And so all the physics of how it goes from that to a phase where they look so different is completely understood, right? So this is what I mean when I say that these are unified in that way. And so the strong force doesn't fit together as nicely. And that's why it has not been fully unified in that sense. And gravity is very, very different because even at this level where I can try to write down a theory that describes the electroweak forces, the way that gravity works is a completely different thing. So in a fundamental physics point of view, the way that gravity functions is very different from how these other forces function. So in that way, in that sense, unifying these two seems to be a very challenging task. And so the applications of it are that well, you've understood how they come together, right? So in terms of practical applications, the unification of electromagnetism with the weak force maybe is not as important because practically the weak force doesn't really help us with anything in our day-to-day life. It just makes the nuclei decay. But for practical applications, maybe the unification of electromagnetism might be the more relevant thing to look at. Because if you think of an electric force that is very different and a magnetic force that is different, then it's not clear how they can function together, right? So it's really a unified theory of electromagnetism that enables us to appreciate that electric fields and magnetic fields are just excitations from one to the other. And so the applications are in every, let's say, electronic equipment that you can see. So these would not be possible without a unified understanding of the electric force and the magnetic force together in the language of electromagnetism. So this is where we really understand how these excitations give rise one to the other. And this in turn helps us understand how, for example, things radiate, how a signal can propagate over space, and all these practical things would not be possible without this unified description.
Thank you. James, you have a question?
I want to ask a question. So in one of your slides, you state that 20% of matter is our matter and it's known, while 80% of this is called dark matter and it's generally unknown.
Mhm.
If it's generally unknown, how did you find, or how did physicists find that percentage in the first place?
Amazing. Yeah, no, I love this question because this really tells you that you're really thinking about the problem, right? So when I say that we don't know of dark matter, I mean that we don't know of dark matter in the same way that we know about these particles. So for all of these particles, right, we know what the mass of each particle is. We know what kind of forces it talks to, and we know how it interacts with all these other particles, right? So for dark matter, we don't know any of this, but we know that it is matter. And so matter by definition is something that has mass, some mass, right? And anything that has mass can talk through gravity. And so we do know of dark matter, and we know of dark matter because it talks through gravity. And that's essentially the only thing we know. So we know that dark matter exists, for example, because it controls how stars move around in galaxies. So if I looked at a galaxy and if I counted up all of the stars that I see there, I can calculate how they will move relative to each other because of the forces from the different stars, right? And if I did this for a galaxy, it would be completely wrong because there's this other kind of matter that is not visible when I look at the galaxy, but it's actually there and controlling how it interacts gravitationally and moves gravitationally. And this was actually the first way that dark matter was first discovered. People were looking at how stars moved in galaxies, and all of the calculations were completely wrong. And then the people realized that if there's this other kind of matter that you don't see that's actually there, then all these observations could be explained. And so we know of dark matter through gravity, but that's the only thing we know so far. And in that sense, we know that it exists, and that also allows us to calculate how much of it is there in the universe. And the answer turns out to be that 80% of the matter is in this dark form, and 20% is in this other form that we can see. But other than that, we don't know any of its properties, right? So we don't know what its mass is. We don't know whether it interacts through one of these forces that we know of. We don't know if it has its own dark force that is not part of the known set of forces. And so all of these other things are still a complete mystery. But we know that dark matter exists in many different solid ways because of its gravitational interactions.
Thank you. Roshni, you have a question?
So I know you've been talking about ripples in space-time and how gravitational waves have sort of like helped us, or research is being done to see how they can trace back to earlier parts of time. It seems like dark matter, all kinds of things are linked by gravity. I was just wondering, I guess it's a multi-part question, but I was wondering what have we seen from gravitational waves so far, like the research being done? And I think I read somewhere that gravitational waves are being researched to see if it's like interdimensional, like if gravity and that kind of the waves can like travel through dimensions. I was wondering if you knew a little bit about that, or if I'm just completely like wrong. Or
That's really interesting because this is actually one of the things I'm working on at the moment, right? So to understand how gravity propagating in other dimensions can affect the gravitational waves that can be detected today. So this is actually a very rich area of research, and gravitational waves are really very, very broadly applicable to anything that happened in the early universe, right? So anything that has mass or energy and moves around in space over time can produce gravitational waves, right? So if you clap your hands, you produce some gravitational waves. And so imagine everything that happened in the universe up until today, right? So everything could have produced some gravitational waves. And so the question really is, are there ways in which you can produce gravitational waves that are so strong that you can actually detect it over all of these other things? Because there's this crazy background of gravitational waves that comes from everything that ever happened in the universe, right? And so for that, you need something that is very energetic. And so, for example, these could be things like vacuum decay, where vacuum changes from one form to the other. And when that happens, you form bubbles of this new vacuum in the background of a false vacuum. And so now I might be talking about things that you don't fully understand, right? But there are these very energetic configurations of the universe going through some stages of the vacuum changing, where you can produce these bubbles of new phases in a background of old phases. So think of it like boiling water, right? So when I'm boiling water, I start with a liquid, but then at some point it goes through a phase transition where it starts bubbling up. And so you have all these bubbles, and the pot of water has a lot of energy, right? And so the universe might have done similar things like this, where it underwent phases, different phases, and it can happen in the same way as water boils and converts from liquid to gas. So then all these bubbles of vacuum can carry a lot of energy, and when they collide, they can produce gravitational waves that are actually quite strong. And so these can happen very generically in all kinds of different kinds of physics setups. So this can be this could be associated with things that have something to do with dark matter. This could be associated with things that have something to do with extra dimensions of space. This could be something that answers one of these other questions, right? About why there's more matter than antimatter, or why neutrinos get their masses in a different way. So all of these different kinds of things can produce gravitational waves. So it's a very it can happen in many different ways. So I could tell you a lot about a lot of different ways, but hopefully that gave you a flavor of.
Ian has a question. Ian?
So you said earlier that there were left and right parts of particles.
Mhm.
What is the difference between those two parts?
I think left-handed and right-handed particles, right? Yeah.
Very good. Yeah, so essentially, the left and the right-handed particles carry different charges under the weak force, it turns out. So they interact differently with the W and Z bosons. And so they have different intrinsic properties of what kind of forces they can talk to.
That's how we know that there are only left parts of neutrinos?
Exactly, right.
Oh, yeah, but
If you could see a left and a right, then you would see for the same particle, two different components, right? So there would be one form of, for example, if you look at an electron, then there's a left-handed type of electron, which interacts differently with the weak force than the right-handed particles. So if you were doing experiments with electrons, you would see essentially two different kinds of electrons that behave in different ways. But we do not see that with neutrinos. We only see the kind that behaves in the left way.
you have a follow-up question?
Yeah, sort of related. What is spin?
Oh, yeah. What is the spin?
Oh no, this is a very difficult question. Where did spin come up?
You haven't talked about it, but we've talked about it in class several times. I've never really.
Spin is a little bit difficult because when you just think of spin, right, you think of a physical object spinning, and in some sense that is also associated with the outcome of experiments. It's essentially how you see particles coming out with what kind of momentum. But when you really come down to the basic idea of spin, it is just really just an intrinsic property of a particle, which tells you how it changes in space and time. So
Actually, that question came up from, like, I mentioned that, like, there are some spin half particles, integer spin particles, and Higgs boson has zero spin, and like, and then actually question came from there, like, why some spin half, some integer spin, and like that. So
yeah, it really has to do with intrinsic properties of particles in space-time. And it's a fundamental property of a particle, just like the charge of a particle, right? So you can't really think of it as a physical object spinning, but really think of it like the charge of a particle that tells you how it undergoes some kind of transformation in space.
Thank you so much. Carmel has a question, like, yeah.
So, I know that with certain quark combinations, they create stable particles like protons or neutrons, but why is it that so far we haven't found any stable combinations of anything other than up, down quarks, or up, down, down? Why isn't there any other sort of particles that we find made up of quarks that are stable, that aren't either up or down?
Mm-hmm. So this is actually a very profound question, right? And so this is really asking you, so usually when something is stable as opposed to unstable, right, there is some kind of underlying symmetry that prevents you from decaying that particle. So if you ask why is the electron stable, then the answer is that it carries some electromagnetic charge and charge is conserved, right? And so then when it decays, it needs to decay into things that are also carrying charge. Otherwise, charge would not be conserved. And if you look at the possibilities for an electron, there's nothing that is lighter than an electron that carries electromagnetic charge. So charge conservation tells you that an electron cannot decay. And then you ask the same question for a proton, right? So then you can ask, why is a proton stable? And so then it comes with this weird combination where three quarks come together into a proton, or a proton. And then you ask, why is it not stable? And the answer is actually not fully understood even by particle physicists. So that is also an open question, because the answer that is given is that it carries something that is called baryon number. And baryon number just happens to be a symmetry of the standard model, just like electric charge. And so then a proton has baryon number, and it needs to, if it decays, it needs to decay into things that also carry baryon number. But the proton is the lightest thing that carries baryon number, and that is why the proton does not decay. But actually, in many theories of physics, in particular theories that look to unify the forces, the proton is actually not stable and it can decay. So it is actually not actually known whether the proton is completely stable or not. And so for these other combinations, to answer your question, there are no symmetries that prevent these particles from decaying. So there's always diagrams you can draw for how they can decay, and they do not violate any laws of physics. And so then that's why they decay.
Maybe one more question. Thank you so much for that. Truman, you raised hand, right? Truman has one question.
Where can dark matter be found? And we have, you mentioned one of the slides that there's machines to measure dark matter, but they actually have.
Where can the dark matter be found? In one of the slides, you mentioned that there are experiments for the detection of dark matter. Have they ever found any? That was the question.
So dark matter can be found everywhere, right? So this is the thing about dark matter, that it is a particle just like these other particles, and it is actually everywhere. So it is actually passing through the room as you speak. If the rule of thumb is that if I hold up my hand like this, at any given moment, there is a dark matter particle inside my hand. So dark matter is actually everywhere, and we believe that dark matter is also on Earth, also on the sun, also in our galaxy. So it is passing through all of us, the reason we don't see them is because they don't interact through any of the forces we know of, right? So it doesn't interact through light, doesn't interact with the nuclear forces. It only interacts through gravity, and gravity is so weak that a single particle will not create enough of a gravitational force to detect it. And that's why you really need to look for other ways of detecting it. And so these ideas of doing experiments like this is that maybe dark matter interacts through some force other than gravity. So what these experiments are looking at essentially is a scattering of a dark matter particle with a particle in the detector, but not through gravity, but through some other force. So maybe dark matter has some very small electric charge that allows it to scatter, right? So these are the kinds of interactions that these people are hoping to see. And to date, we have not seen any conclusive evidence that anything like this has ever happened.
Okay. Maybe it is the like, oh yeah, like one more question. You have one more question?
Yeah.
Yeah.
So is it like thought that I feel like there's like a common reference of the fabric of space-time that holds objects with greater mass and then creates like orbits and stuff. Is that thought to be dark matter? That's holding us like together.
The question is like you're talking about like the creating the orbits in space and time.
Space time, yeah. I think
orbits in space and time. Actually, that's what that was in the presentation, right? Yeah. Actually, that question was already answered, by the way. Roshni is just confirming that. So if you see any object going around the vast space and time, then that is sort of kind of an indication of dark matter.
So dark matter can affect that, right? So I think what the question was whether you can infer this motion as being caused by dark matter, right? So whether the bending of the fabric of space and time due to massive objects can be explained by dark matter in some sense, or whether dark matter has anything to do with that. Am I right? Was that the question?
Right.
Yeah, so there are actually some theories called the modified gravity theories, right, or MOND, which claim that some effect like this could explain dark matter. And this kind of theories were very popular a few decades ago, but now that we've done more and more experiments, it seems that these kinds of theories cannot explain everything. So dark matter really is most likely just a particle, just like the other forces, rather than some effect of the fabric of space and time.
Dr. Shakya, one final question. You answered so many questions beautifully.
Really up to you.
Here is one question from Truman again.
This might seem like
like a silly question, but if the only force that we know dark matter can interact with is gravity, and you're looking at how gravity might be able to propagate through different dimensions, how do we know dark matter isn't just from another dimension? It's not actually in like our dimension.
No, indeed. And actually one of the most popular theories for what dark matter is that dark matter is an excitation of the particles we see in a different dimension. So think of an electron, right? So if I could give an electron some energy and that energy propagated in a different dimension, then it would just look like a lot of energy where an electron is, and that would behave exactly like dark matter. So indeed, that could be one of the possibilities for what dark matter is.
Okay, great. So let's thank the speaker one more time.
Thank you, everyone. Great questions.
Yeah, thank you so much. Have a good night.
Very happy to do this. Thanks.
Thank you.
Thank you.
Thank you.